In the name of Allah, if we have a power transformer in a substation and this transformer was disconnected for maintenance work, for example, and after completing this maintenance, it is required to reconnect the transformer, energize it, and return it to service. We may find, for instance, that when the transformer is energized, it trips immediately. Naturally, we find that the protection device responsible for tripping the transformer is the differential protection relay. Of course, we all know that this tripping is often due to the occurrence of magnetizing inrush current inside the transformer. Typically, we may wait for a minute or two and then attempt to energize the transformer again. As a result, the transformer may accept the energization, or unfortunately, it may trip again and fail to remain connected, and this process may repeat. So why does the transformer sometimes accept energization on the first attempt? And why might the same transformer only accept energization on the second, third, or even fourth attempt? That is why we are going to talk about the magnetizing inrush current, or the inrush current in transformers. We will learn together the main causes behind the occurrence of inrush current, whether it is a single type or if there are different types of this current, and how we can address or avoid the problems caused by this current. As we will see together, or as we all know, the inrush current typically occurs at the moment of transformer energization. However, the important question is, can magnetizing inrush current occur while the transformer is already in service and operating, or does it only happen at the moment of initial energization? Certainly, this current or inrush current can actually occur even when the transformer is in service. But how? We will find out together in this lecture. To begin with, we must understand that one of the most abnormal phenomena that power transformers are exposed to is the occurrence of magnetizing inrush current. This current is of course transient, random, and lasts for a very short period of time. For those who wish to study this topic in more depth, they can refer to the standard IEC 600768. The second point is that the magnetizing inrush current occurs at the moment the voltage is applied to the transformer or at the moment the primary windings are connected to the power supply. Naturally, this current appears as if a short circuit current has occurred inside the transformer. Now we want to understand how this phenomenon actually occurs in a clearer and more systematic way. As we can observe, there is a power transformer located in a substation, and this transformer is in service. That is, it is energized. In other words, the primary side of this transformer is connected to the power supply or the main bus bar, and the secondary side of this transformer feeds various loads. Let us assume, for example, that it is required to disconnect this transformer for maintenance work or for testing or for any other work that will be carried out on this transformer. Of course, we all know that the disconnection process starts by disconnecting the loads first, followed by disconnecting the transformer from the secondary side, and finally disconnecting the transformer from the primary side. Now let us assume that the maintenance work, testing, or any other required activities on this transformer have been completed, and it is now required to re-energize the transformer, reconnect it, and return it to service once again. Of course, we must understand that the steps for energizing a power transformer are the reverse of the steps for disconnecting a power transformer. This means that in order to energize the transformer, apply voltage to it, or return it to service, we must begin by connecting the primary side first. Let us focus carefully on this point. The moment we connect the primary side of the transformer or apply voltage to the primary side, we will observe the occurrence of a very large current flowing inside the transformer. This current appears on the protection devices as if it were a short circuit current or an internal fault within the transformer. Unfortunately, the protection devices will immediately trip the transformer since they detect what seems to be a large short circuit or fault current inside the transformer, even though at this point the secondary side is still disconnected and there are no loads connected to it. Naturally, this large current is the magnetizing inrush current, which is essentially a no-load current, and its value can exceed more than 10 times the rated full load current of the transformer. As I mentioned earlier, this magnetizing inrush current occurs only in the primary windings, and of course, it decays quickly with a rate of attenuation that is inversely proportional to the power rating or the rated capacity of the transformer. It is also important to understand that the phenomenon of magnetizing inrush current is a random phenomenon, meaning that it does not necessarily occur every time we energize the transformer. And even if it does occur, it does not necessarily have the same current magnitude, even if it is the same transformer and the same power supply source. And in order to understand what it means for the magnetizing inrush current to be a random phenomenon, and why it does not necessarily occur every time we energize the transformer, we must first review and understand some very important points. Of course, we all know that the network voltage is alternating voltage or alternating current, which means that the voltage value is always changing. In other words, the value of the network voltage at moment t1 might be a positive value, the value at moment t2 might be 0, and the value at moment t3 might be a negative value. Therefore, we can understand from this that the value of the network voltage is constantly changing at every instant, whether it is a positive value, a negative value, or 0. Now we are saying that the phenomenon of magnetizing inrush current is a random phenomenon and does not necessarily occur every time the transformer is energized, and even if it does occur, it does not always have the same current magnitude each time. So how is that possible? We must understand that the fundamental factors behind the occurrence of magnetizing inrush current and the maximum value this current can reach depend on three main factors. The first factor is the value of the network voltage at the moment of transformer energization. In other words, as I mentioned earlier, when we energize the transformer, the voltage at that exact moment may be positive, negative, or 0. Of course, this occurs randomly and is not controlled or known in advance. The second factor is the value of the residual magnetism or remnant flux in the transformer core at the moment the transformer was disconnected from service. We must note that this factor relates to the moment of disconnection, whereas the first factor relates to the moment of reconnection. The third factor is the polarity between the residual magnetism in the transformer core at the moment of disconnection and the network voltage at the moment of reconnection. That is, whether one is positive and the other negative, or if both have the same polarity. Therefore, we must understand that the main reason behind the presence of magnetizing inrush current is the interaction between the supply voltage applied across the primary winding of the transformer and the magnetic flux density inside the iron core or within the magnetic circuit of the transformer. Of course, we all know that under normal operating conditions of the transformer, the magnetic flux wave lags behind the voltage wave by a phase angle of 90 degrees. As I mentioned, this is in the normal case or under standard operating conditions of the transformer. As we can see, the magnetic flux density varies with time in the form of a sine wave, just like the voltage waveform. From this, we understand that the magnetic flux density can also be positive, negative, or 0, depending on the moment in time. Accordingly, when the transformer is disconnected, the iron core retains a certain amount of magnetism or magnetic flux density, which we refer to as the residual magnetism in the transformer core. This residual magnetism may be positive, negative, or 0, depending entirely on the exact moment the transformer was disconnected from the network. For example, as clearly shown here, it is possible to energize the transformer when the voltage value is at its maximum positive value and the magnetic flux density is 0, meaning there is no residual magnetism in the iron core. Or the transformer can be energized when the voltage value is 0, but there is residual magnetism at its maximum positive value. Or, for example, the transformer can be energized when the voltage value is 0 and there is residual magnetism at its maximum negative value, and so on. We emphasize once again that there is a phase angle of 90 degrees between the voltage and the magnetic flux density under normal operating conditions. This is the case in normal operation only. However, in the transient condition, we find that the phase angle is random, with no specific value, In general, there are 6 conditions or factors that can lead to the occurrence of magnetizing inrush current. 1. Energizing when the voltage is 0 and there is no residual magnetism in the iron core. 2. Energizing when the voltage is 0 and there is residual magnetism in the iron core at its maximum negative value. 3. Energizing when the voltage is 0 and there is residual magnetism in the iron core at its maximum positive value. 4. Energizing at maximum voltage with no residual magnetism in the iron core. 5. Energizing at maximum voltage with residual magnetism in the iron core at its maximum negative value. 6. Energizing at maximum voltage with residual magnetism in the iron core at its maximum positive value. However, in brief, we want to understand together what the worst case scenario is for energizing the transformer and what the best and most ideal condition for energizing the transformer is. In brief, the worst case scenario for energizing the transformer is the first case, energizing the transformer or connecting the primary side of the transformer when the voltage is 0 and there is no residual magnetism in the iron core. In this case, the transformer will undergo a transient period, resulting in a magnetizing inrush current with a very large value. However, the best and most stable case for energizing the transformer is the third case, energizing the transformer when the voltage is 0 and there is a residual magnetism in the iron core at its maximum positive value. The shape of the magnetizing inrush current is shown in front of us, and as I mentioned before, it is a distorted wave that contains second and third harmonics, and so on, in addition to the DC component of the current. As we can see, the current for each phase is different from the other phases. Of course, the difference in the shape and value of the magnetizing inrush current for each phase occurs because, as we know, at any given moment, there will be a difference between the voltage values of phase R, phase S, and phase T. Since there is a difference in the voltage for each phase, it means that there will also be a difference in the magnetizing inrush current for each phase. At the beginning of the lecture, I asked a question. Is it possible for magnetizing inrush current to occur while the transformer is operating, energized, supplying loads, and in service? And of course, we said yes, it is indeed possible for magnetizing inrush current to occur while the transformer is in service, but how can this happen? Let us assume we have a substation containing, for example, 4 power transformers, and as we can see, transformers number 1 and 4 are connected to bus bar number 1, while transformers number 2 and 3 are connected to bus bar number 2. Let us assume that due to any emergency situation, a short circuit occurred or a fault happened on bus bar number 1, or there was a voltage dip on bus bar number 1 for any reason or due to any transient condition. This of course means that the voltage on bus bar number 1 will drop to 0 for a short period of time, after which the voltage on bus bar number 1 will return to its normal value, and all of this happens within a very short time period. Naturally, the fact that the voltage disappears or drops to 0 on bus bar number 1 and then returns again means that we have essentially performed a re-energization of transformers number 1 and 4. And as long as the transformers have been re-energized, then of course it is very likely that a magnetizing inrush current may occur due to the disconnection and subsequent reconnection of the transformers. And the magnetizing inrush current in this case is called the recovery magnetizing inrush current. The second point, as we can see in front of us, is that if we assume that transformers number 1, 2, and 4 are energized and in service, and transformer number 3 is disconnected, then it is required to connect transformer number 3. Of course, transformers number 2 and 3 are connected to the same distribution bus bar number 2, and therefore we will notice that when transformer number 3 is energized, a magnetizing inrush current may occur in transformer number 3, as we all know. However, the surprising thing is that upon energizing transformer number 3, we may be shocked to observe the occurrence of magnetizing inrush current inside transformer number 2, even though transformer number 2 is already in service, energized, and supplying loads. This happens due to the DC component present in the magnetizing inrush current of transformer number 3. The DC component causes magnetic core saturation in transformer number 2 because it is either physically close to transformer number 3 or connected in parallel with transformer number 3. Of course, the magnetizing inrush current in this case is referred to as sympathetic magnetizing inrush current. Therefore, we can say that there are 3 types of magnetizing inrush currents. The first type is the original magnetizing inrush current, which we are all familiar with, and which occurs at the moment the transformer is energized and connected to the network. The second type is the recovery magnetizing inrush current, which occurs when a transformer is unintentionally de-energized and then re-energized in a very short time due to transient events on the power system. The third type is the sympathetic magnetizing inrush current, which occurs in a transformer that is already in service and energized as a result of energizing another transformer connected in parallel or located nearby. Before we talk about the most important solutions to overcome the phenomenon of magnetizing inrush current, we will briefly and quickly discuss the key observations related to magnetizing inrush current. The first point is that the value of the magnetizing inrush current is approximately 10 times, or roughly between 8 to 12 times, the rated full load current of the transformer. The second point, as we mentioned earlier, is that the magnetizing inrush current is a distorted waveform that contains various degrees of harmonics, such as the second harmonic and third harmonic, in addition to the DC component of the current. The third point is that the phenomenon of magnetizing inrush current occurs more prominently in new transformers than in older ones. This is because a newer and more modern magnetic core can retain residual magnetism more effectively than older transformer cores. The fourth point is that since the magnetizing inrush current can reach up to approximately 10 times the rated full load current of the transformer, this results in mechanical stresses on the transformer. These stresses can lead to the displacement of internal windings from their original position, potentially causing short circuits between the windings themselves, between the windings and the magnetic core, or between the windings and the transformer tank. Of course, we must understand that one of the most important protection devices on power transformers is the differential protection relay. As we all know, the operating principle of the differential protection relay is to compare the current in the primary winding with the current in the secondary winding while taking into account the transformation ratio of the transformer based on the voltage values on both the primary and secondary sides of the transformer. Since magnetizing inrush current occurs only on the primary side of the transformer, this means the differential protection relay will be activated, causing the power transformer to trip on both the primary and secondary sides. This happens because of the inrush current in the primary winding only. It's important to note that the differential protection relay may cause an incorrect trip of the transformer, as the trip is triggered by the magnetizing inrush current and not by a fault or short circuit inside the transformer. As we mentioned earlier, the phenomenon of magnetizing inrush current is considered a normal, transient phenomenon within transformers, which vanishes within a very short period, typically not exceeding 1 second or slightly more. We have understood together the dangers of magnetizing inrush current on the transformer, but now we want to know what are the treatment methods or suitable solutions, or how we can overcome the problem of magnetizing inrush current. The first step is, if the transformer needs to be disconnected for any maintenance, testing, or other work, we must first disconnect all the loads from the secondary side of the transformer. Then, the next step is to disconnect the current breaker on the secondary side, and the last step is to disconnect the primary side current breaker from the main bus bar that feeds the primary side of the transformer. The second and most important point is related to the protection device of the transformer. As we mentioned earlier, magnetizing inrush current is a distorted waveform that contains harmonics. The key point here is that when we analyzed this distorted waveform, we were surprised to find a large percentage of second harmonic components, which can be as high as 50% or more. However, the percentage of second harmonic components in a short circuit current is no more than 7%. Thus, we can take advantage of this large percentage of second harmonic and distinguish whether the large current that occurs in the transformer is magnetizing inrush current or a short circuit current due to a fault. This distinction is a feature available in the differential protection relay of the transformer. Therefore, we can use this discrimination feature to prevent the differential protection relay from tripping in the event of magnetizing inrush current. As we said, all of this depends on the percentage of the second harmonic present in the large current when the transformer is connected to the service. Thank you for your attention. See you in the next lecture.